Okay. So the next thing is I just wanted to check in and see if anyone has any sort of larger scale questions about the problem set that is due this evening. Anything that might interest the class to hear about. You still have my office hours from 3:30, or probably like 3:35, because we're interviewing a new professor like until 3:30, so maybe a couple minutes after that, until 4:30 today. So do feel free to drop into Zoom. But does anyone have any general questions on that? Anything at all? A couple of good ones in Slack so far, so I appreciate that. Okay. All right. So sort of a general announcement before the next couple days. We've moved into this segment of the class thinking about hill slopes, right? Or all those places on Earth's surface that are not rivers, basically, right? Places where the land may be sloping, but flowing water is not the norm. And this is going to require, not so much today, but starting next time, some math, right? So you know this class sort of alternates between like nice pictures of pretty places and big bad sets of equations. And today we'll mostly be on the picture side of things, and next Tuesday we'll be more into the equation side of things. So with that in mind, I would highly recommend that next Tuesday is like a great day to show up in person, because we're going to be doing a lot of the math, and I think it'll make more sense in the moment than on the recording. But with that in mind, let's get back to this discussion of what shapes landscapes aside from flowing water, right? We've spent most of the semester on how flowing water shapes river channels, and now we want to think about how all the rest of the landscape gets shaped, how basically everything here that we see outside of the valleys came to be and came to take its shape. So we want to think broadly about this question of how hill slopes change their shape through time. Again, here looking at the Gabilan Mesa site in California for kind of an extreme example of what those landforms look like. Last time we talked about the processes that stress rock, or that basically, in other words, cause rock to break into smaller pieces, ultimately becoming soil or sediment or something that's mobile, right? So what were some of those processes that we talked about last time? Kind of jog your memory using the pictures along the bottom here. What were some of those soil production or weathering processes? Thermal weathering, right? So got the hot sun right there, right? When you heat up rocks, different minerals have different coefficients of thermal expansion. They expand at different rates. Differential expansion of minerals causes the initiation and propagation of cracks within the rock, right? You crack a rock enough times, you end up with sediment. That's probably what's going on here with this boulder out in the Sierra Nevada foothills. It's exposed to really wild thermal cycling, really hot highs during the summer day, really low lows at night, and that leads to cracking that ultimately causes pieces of rock to break away. Okay, so thermal weathering, what else?
Freeze thaw.
Freeze thaw, right? We've got a picture of some ice right here. This idea that ice or water, H2O, is a pretty unique molecule in that when it freezes or when it becomes a solid, it actually expands, right? Ice cubes float in your drink, telling you that ice is less dense or more expanded than the equivalent amount of water. So what happens is water will trickle into some pre-existing crack or gap in the rock. It will then freeze, which will cause it to expand by about 8 to 9%, I think is what we settled on last time, which will ultimately wedge that crack open a little farther, and this process can repeat over and over again. So this typically happens in places much like our home here, where we have a lot of days that cycle between sub-freezing and over-freezing temperatures, right? That's the big ingredient for efficient frost cracking. You also have to have water, right? So there's that. Okay, what else? Thermal expansion and contraction, frost heaving, what else?
I can't really remember the name, but the rock gets wet and then it dries and then it expands and it shrinks.
Yeah, perfect. So often people just call that like wet-dry cycling, right? Which is the easy word. The jargon word is slaking, right? That people use for that process. And the idea, much like with thermal weathering, is of course that when you get different minerals wet, they expand or contract by different amounts, and ultimately they cause stresses within the rock due to that differential expansion and contraction. You wet and dry a piece of the bedrock from around here enough times and it'll just fall apart, which happens like all over my neighborhood. Okay, so we've got thermal weathering, we've got frost cracking, we've got slaking. What else? What's the other thing pictured here? Maybe the most obvious one.
Plant weathering?
Right, weathering driven, or the breaking apart of rock driven by plants. And what's kind of unique about plant-driven weathering relative to the others?
It's chemical and physical.
Right, there's sort of two mechanisms, right? Chemical and physical weathering. So the physical part, which is the sort of really obvious one, right, is if a root grows into a crack in the rock, the root grows thicker and thicker over time and will pry that rock apart, right? Pretty intuitive, not that complicated. What is the mechanism? And maybe someone from the Davis College could chime in here. What is the mechanism behind plant-driven chemical weathering of rock? Not something I really know a lot about, to be honest. What is the mechanism there? What happens?
Does the plant access all the nutrients that are in that mineral and uptake it?
Yeah, exactly. So plants, the critical mechanism, right, is that plants are basically secreting acids, and the goal is to dissolve out minerals that they want to eat, right? I don't know, things that are in rock, commonly potassium, calcium, sodium, right? All these cations that plants need. Plants will secrete acid to liberate those from the rock, to eat them, and that breaks down the rock chemically, right? So plants are weathering rock both physically and chemically. So we've got all these processes that convert rock into soil, right? And ultimately break the rock down into little pieces that can move. And so, again, this question that we want to now move to, which I think is more exciting than weathering processes, to be honest, is given that you have some of that sediment that's been produced, that you're not in a totally bedrock or sediment-starved landscape, how do hill slopes change their shape through time? How does sediment transport on hill slopes work? And so today we'll be talking about kind of the mechanisms by which that occurs. And then next time, or we may start a little bit today, we're going to dive into the mathematics of how we use that to think about how landscapes change over time. So we can think of this broadly in two categories, right? What if I were to say, like, what is a fast mechanism of hill slope erosion or evolution? Like, what kinds of processes cause a big change in the shape of the landscape, like in the blink of an eye, that even humans can observe? What would a fast process be that changes hill slopes? We discussed this a little bit last time.
Landslide?
Yeah, a landslide, right? Or some sort of mass movement. Maybe it's a rock fall, landslide, doesn't matter what you call it. And we're going to get there. We're going to study those fast and threatening processes in great detail in just a week or two. But for today, we're going to focus on those ones that are sort of out of the envelope of human perception by and large. So those slow hill slope sediment transport processes that are active every day, but whose effects are only sort of tangible as they add up over geologic time. So let's think about some examples of that. We talked about one early on in the class, and that was related to rainfall, right? How might rainfall, even when we're not talking about sort of water flowing over Earth's surface, how might rainfall move sediment on a sort of small and slow scale? What might rainfall have to do with all of this? I have a video for that. Okay, so we're going to watch a raindrop hitting a bed of sediment, right? This was done in a laboratory. Oh, let me turn these off. This was done in a laboratory, and we're going to watch it in slow motion. So what's happening right here? What has happened now that this raindrop, and this happens a gajillion times every time there's a rainstorm, right? What has happened to this raindrop hitting Earth's surface? What's going on here? What's happening to the sediment? It's being moved, right? The rain is actually striking with enough force to move these little, in this case, glass beads, because we're in a lab, but this happens equally well out there in nature to little soil particles, right? So we've got some impact, like a little tiny bomb hitting Earth's surface, and we've got sediment being splashed in every direction, right? So this is a phenomenon that we call, pretty sort of intuitively, rain splash. Right, so that's sort of one of our slow or sort of non-catastrophic hill slope processes is rain splash. And that's the idea that when a raindrop hits the ground, you splash a bunch of sediment up and it moves some distance. It's a small distance, right? You're not going to observe this like over one rainstorm. It's going to add up over geologic time. So what was true in that video? When the raindrop hit the sediment bed and the sediment started splashing out everywhere, in what direction did the sediment move? Or directions did the sediment move? Outward, right? In every direction, right? Like 360 around our impacting raindrop. And the raindrop was impacting a flat surface, right? So if I draw a little sketch of what was going on, we have some relatively flat surface. We have some impending raindrop that hits that surface. We saw the sediment go outward in every direction. So, given that this surface is flat, the question I'm trying to get at here is there a preferential direction for sediment transport? Like, is our rain splash driving more sediment transport in any one direction? Or is it all kind of equal? Equal? Yeah? Anybody else? Equal? Right, it's a flat surface, right? So any grains you displace in this direction are going to go the same distance on average, right, over the thousands of little pieces that are moved as in this direction. So when rain splash impacts a flat surface, on a flat surface, there's equal transport in all directions, right? And I've only drawn two directions because I'm working kind of in a two-dimensional world here. But this, of course, applies to the other direction into and out of the board as well, right? So when rain splash hits a flat surface, it just moves some stuff, but you can envision a situation where there's like tens of thousands of raindrops coming down onto the surface, and they're all moving sediment around to the left and to the right. Does anything happen, like on average? Is there any meaningful change done, like over the course of 100,000 raindrop impacts in this situation on a flat slope? No, why not? Yeah, because everything's just moving around left to right. You've got one over here that's putting stuff back in here, same over here, right? And it all just averages out over a rainstorm, over a rainy season, over a decade, whatever. So now, my question for you is, what happens when we have a sloping surface, some hill slope, right? Nature is rarely perfectly flat. And we have a raindrop that impacts that surface. What happens now? In which direction does sediment move farther when it's displaced by this raindrop? Okay, I see a couple of, everyone just point, like which direction? Okay, so why is that? We're all in agreement. Why? So if I draw arrows, right, I can say, well, the sediment is going to move farther in this direction than it is that way, right? So why is that? You're all correct. Just why? What's the mechanism for that?
Gravity.
Gravity, right? And, you know, sort of the geometric constraint that, like, there's a piece of hill here blocking the way, right? So sort of a combination of those two things, right? Broadly, a raindrop is going to displace some amount of sediment. If it's going uphill, it's basically blocked by the topography. If it's going downhill, it's following the pull of gravity, which is good, allows for more efficient transport, and there's just more room to maneuver in that direction because there's no topography getting in the way. So now let me ask you, if we have 1 million raindrops in a big rainstorm hit this surface, what is the net transport direction? Like, what is the overall change that's going to occur from those millions of tiny little impacts? What's going to happen as a result of all of these little biased impacts added up together?
Sediment's going to move downhill.
Yeah, we're going to have net downslope sediment transport, right? Net downslope transport. So on a sloping surface, there is net downslope transport. And again, this feels almost silly to discuss, right? Like it's one raindrop moving these tiny little pieces of sediment. The important thing is that over geologic time, there's tons and tons of raindrops, right? One storm is tons and tons of these impacts, and it adds up over time, like Isaac said, to net downslope transport on a sloping surface. So that's one of these slow or creeping hill slope processes, right? And we call this a creep-related process because the actual sediment transport distances are barely measurable, right? You might move a sediment grain like a micron or 0.5 millimeter with one of these rain impacts. But over geologic time, they add up to meaningful net downslope transport. Okay, so that's rain splash. What might be another mechanism for downslope transport? What happens when a tree falls in the forest? Whether or not there's someone there to hear it. What's happening down here?
The roots are being like pulled outside, like leaking into the soil.
Yeah, so and I would say even more obviously, the roots have grabbed on to like a huge ball of soil, right? And ripped it out of the ground. So we typically call this tree throw. I'm not exactly sure why. I mean, I guess it's like kind of throwing sediment. I don't really know why that is. Tree throw, which is this idea that tree roots dig down into the soil, and when the tree falls, as all trees must inevitably do at some point, they pull that soil and move it to some degree, right? So let's sketch out how that would work out on a flat land surface. We've got some flat surface. We've got some tree and it's got roots, right? Some big root network. So when that tree falls, there's some clump of soil, right? Some section of soil that these roots have grabbed onto. And when that tree falls, ultimately what we're going to have is some giant hole in the ground and then a root ball covered in dirt. Oh no, what did I do? Okay. A root ball covered in dirt. If the tree kind of keels over this way, we have some tree root ball covered in dirt and some empty hole, right? So sediment has been transported here. But let me ask you again, like if I have a flat surface, some perfectly flat plain with a forest on it, I don't know, think like what you see in like coastal Carolina or something, right? Some really flat plain with a big forest on it. And all those trees, you know, every 50 or 80 years, one of them falls down, and it might fall to the left or it might fall to the right, and it moves sediment a little bit one way or the other. Are we adding up to make any overall geomorphic change, any overall sediment transport? Flat plain, trees falling, sometimes one direction, sometimes the other. Do we have any net sediment transport in one direction or the other?
No.
Okay, I see head shaking, which is good, right? No net transport across a flat surface. So on a flat surface, so tree throw is a little different, right? On a flat surface, any one tree throw event will move sediment in any one direction a little bit, whichever way the tree falls. The important thing is when this is added up over a meaningful number of events, there is no preferential transport direction, right? Like over time, another tree will fall in such a way that it will return sediment to this hole, and that'll just continue forever. So on a flat surface, equal transport in all directions when integrated over time, right? Over many tree falling events. But now let's think about a tree on a slope. And I'm going to draw a little smaller because I made that one too big. So a tree on a slope, it's got some brush, it's got some roots. So a couple of things are now true about this tree. First of all, which way is it more likely to fall when it dies? Downhill, right? So first of all, trees are more likely to fall this way because trees tend to basically lean out from the hillside. It's likely to fall downslope. Second thing, what is true once that tree has fallen, right? Again, we have some patch of soil that tree has basically glommed onto. And then after it has fallen, we have our same hill slope, but we have a big pit, and then we have this root ball covered in soil, and of course the tree trunk is like, this is really testing my artistic abilities. We have the tree, which is down here. So we've moved sediment downslope, right? This sediment used to be here, and it's moved there. So not only are trees more likely to fall in that downslope direction, but when they do, they move all of that sediment in one preferential direction, and again, it's downslope. So what happens over time when we integrate over many tree falling events? What happens? Where is sediment preferentially being transported? Downhill, right? So the lesson here is that regardless of the forcing, regardless of the cause, whether it's raindrops or trees, and we'll do one more quick example that I think is really fun. When they're occurring on a flat surface, you don't have any net or over time or time integrated soil flux or soil transport in any one specific direction, right? You just have soil moving around, filling in the places it was taken from and going back and forth, maintaining a flat surface. When any of these processes act on a slope, you have biased transport pathways and you have net downslope transport, right? So again, here we have this net downslope kind of looks like I wrote clown slope transport, which would also be interesting. Transport, net downslope transport, right? So whether it's rain, whether it's trees, whether it's something else, we're in a situation where the existence of some topographic gradient, some slope, allows us to know that we're going to have net soil transport when averaged out over many creep or disturbance events over geologic time. That net transport will be in the downslope direction. So let me give you a couple more examples of that, and I think the story will become familiar. But this one's pretty cute, so I like this one. What about burrowing animals? What if we have like a flat surface? Well, that's not really flat, but just assume that it is. And we had like a little bun on that surface, and it's like, I'm going to dig a home, right, in a hole. I'm going to dig a hole. And so it digs a hole, so that's its house, and then it kicks up sediment in one direction or the other, doesn't matter, kicks up some pile of sediment out of the hole that it's dug, and we have some sediment transport. But if over geologic time we have like 100,000 bunnies living out their lives and making homes on this flat surface, how is this surface going to change in aggregate on average over geologic time? This flat surface.
Can those holes fill up with the burrows of sediment?
Yeah, so I think you're on the right track, which is to say that it's not going to change on average over time, right? You might have one bunny dig over here and kick some sediment up in these directions, and then have another one burrow here and kick sediment back into this hole. And because the surface is flat, it doesn't matter how many like bunny family home building events you integrate over, you're always going to be talking about a flat surface that experiences no net or no directed transport, right? So no, another way to say that would be that there is no preferential transport direction. Because the surface is flat, you're equally likely to have these particles kicked in any one direction. When you dig a bunch of bunny houses, you just average out that transport over time. So I think this is going to start to feel repetitive, so this is the last one I'll do. What happens when our bunny, or whatever it is, maybe that's like a cat. Anyway, it doesn't matter. When that animal decides to burrow on a hillside, it's like, okay, I actually want to make a house here. Which direction is sediment likely to be preferentially transported if it's just kicking that stuff out of the hole? Downhill, right? Always downhill. Correct answer. There may, of course, be a little bit of sediment kicked up in this direction, but we've got gravity on our side. On average, the transport distances are longer downhill, and there is net downslope motion, right? So again, if you have 1 million bunnies digging 1 million holes, this will add up to net downslope motion. So these are the class of processes that we call creep processes, right? They're operating too slowly for us to go. We can watch one bunny dig one hole, but it's not going to tell us that much about average sediment transport patterns, right? They're only geologically important when they're integrated over time. So when we think about these processes, we're always thinking about their time-integrated effects. Not so much what does one raindrop do when it falls on sloping topography, not so much what does one bunny do when it's digging a hole, but what do these effects add up to over time? And the answer is that when these effects are acting on a flat surface, nothing much happens, right? You're just making little pockmarks in the topography and filling them in again, and it's all kind of the same. When you have a sloping piece of topography, or a hill slope, right? This is what we're after learning about. You have net downslope motion as the accumulated product of years and years and years of these creep processes. Okay, one last one. Has anyone ever seen, like, if you go out for a hike or something like that when it's been really cold, has anyone ever seen ice lensing in the soil? Like when the soil gets these ice needles kind of within it? Has anybody seen that? Yeah, so it's really common around here, especially if you hike, I don't know, like by a stream, like at Tom's Run, you would see this, or other, like at Cooper's, you know, it's often common. So think about what that ice lensing is doing to the soil, right? This is effectively from water in the soil column freezing. But if you ever noticed like what that does to the soil, how it changes things, like what is that ice lensing doing? When you look at one of those things, or when you pick one of those pieces up, what has it done to the soil? Has it changed the structure of the soil at all? Changed the surface at all? I wouldn't blame you if you never bothered to investigate this, but we will watch a video of a very nice man on the internet who has. So this is going to go by fast because it's truly just like some rando in his yard. This is not a science video by any means, but he's going to narrate it for us. So he's like in his yard, he's looking at some of these ice needled or ice lensed patches of soil, and we're going to see what he says.
This is called ice lensing. So you've got these vertical fibers that have grown. See how this is vertical? So the ice is actually growing, and it's really pushed up bits of the soil by quite a lot. Like you can see how tall these things are. So just in that one little bit, it's lifted the topmost bit of soil by about a centimeter.
Okay, so that's the key part, right? So what is this process of ice growth in the soil doing? From what we care about as geomorphologists, what is it doing to the sediment or to the soil? It's moving it, right? It's moving it in what direction? Up, exactly, right? You've got ice growth, ice expands relative to water, so it poofs up the soil. And he said in this case, about a centimeter. We won't quibble with that, that's totally fine. So this gives us another example to think of how these transport processes act on some existing piece of topography. And I promise we'll end it here. I won't discuss another one of these, but let's think about this ice lensing on a flat patch of ground like that guy's yard. So he called this ice lensing. We could use the broader category of terms and call that something like frost heave, right? Which is like when you have damage to it, to your house from this process, they call it frost heave. Doesn't really matter. So we get some freezing event, right? And there's water in the soil, and that causes sediment to poof up by some amount, right? The ice pushes that soil upward, and then what happens when the ice melts? Like when it gets warm. What happens to that sediment that's been pushed a centimeter upward towards the sky?
Does it just go right back down?
Yeah, it just falls right back down to where it was, right? Just straight back down. So has any net sediment transport occurred after one of these cycles of frost heaving on flat ground? No, you're shaking your head, that's exactly right. No net sediment transport has occurred. So again, the story is the same. On flat ground, sure, sediment is moving. There's cool stuff going on, depending on whether you think that's really that cool or not. But there's no net sediment transport. It's just getting puffed up. It's falling back down. And it wouldn't matter how many of these cycles we saw on flat ground. It would just vibrate a little bit, might wreck a house foundation, might wreck a road, but the overall topographic surface would just be what it is. Okay, so now, for all the marbles, what happens when we have this process of ice lensing or freezing of the soil acting on sloping ground? And there are a couple pieces to unpack here. First of all, which direction, like what arrow should I draw to indicate which direction the ice pushes the soil? Perfect. So what's the geometric term for that? Like what should I draw? How is it oriented relative to the soil? Yeah, perpendicular to the land surface, right? So the soil is sloping. Broadly, the freezing pushes particles of soil perpendicular to the land surface. That's exactly right. And now, what happens when it gets warm? Wait, are you pointing downward?
It melts down the slope.
Yeah, so the water melts, and then these sediment particles fall. And what direction do they fall? Do they fall back right along these arrows, back to where they came from?
They fall straight down.
They fall straight down, right, in line with gravity. They fall towards the center of the earth, right, along the gravity vector. So what that looks like is a mess to draw, if I'm honest, but it looks something like this. So for every cycle of frost heaving, or of ice lensing, you poof up soil particles perpendicular to the surface, which is no longer purely vertical because the surface is no longer purely horizontal. But then when it melts and when that cycle has ended, the sediment grain or the piece of soil falls vertically, right? As it must by the laws of gravity if it's not being disturbed by any other force. And so slowly each particle walks downhill, right? That's what's going on. Now if you have these cycles day after day after day, winter after winter after winter, year after year after year, you get basically soil walking down slope, and you again have what? You have net downslope soil transport. Net downslope transport. So the fundamental point here is that for any process you can envision that might move sediment that's not due to, say, flowing water or wind or something like that, right? Any of these local, small-scale, what we might call creep and heave processes, for anyone that you can envision why, when it's acting on flat ground, there isn't really a geologic, or there isn't sort of an effect on the geomorphology over time. There isn't an effect on the shape of the land surface over time. And you can equally well envision how when that process is acting on a slope, there's a transport bias in the downslope direction, right? Our sediment transport pathways are biased in a downslope way, leading to net downslope transport of sediment. Meaning that the key control on how quickly sediment moves downslope, assuming these processes are acting equally in any given landscape, is the slope itself. So let's think about that for a second. Ooh. So we want to understand how, and we'll label the quantity on the y-axis in a second, but conceptually we want to think about how the amount of sediment moving down slope, right? How the amount of sediment moving through our system, our hill slope, depends on slope, or on the slope of the topography. So what did we already decide about a slope equal to 0? Integrated over time, what is the transport rate, or the amount of soil moving across a slope of 0?
0.
It's nothing, right? Exactly. There's nothing moving. Right? So at a slope, at a slope of 0, we can say that our mystery quantity here, the amount of sediment that's moving down slope, is 0. And then what's the trend look like? Like, what happens as slopes increase? How does our quantity of stuff we can move scale with slope? Do increased slopes what do they do to our ability to transport sediment? Obviously culminating in things like landslides, right, that happen very catastrophically.
It increases.
It increases, right? That's really all I'm after here, is that as our slope increases, our ability to transport sediment efficiently downslope also increases, largely because of the contribution of gravity, right? We can think about two cases. We can think about a low angle hill slope and a high angle hill slope. One of those is going to have a greater contribution by gravity to all downslope sediment transport, right? And it's this high angle hill slope. The hill slope angle is closer to the gravity vector, right, which is of course vertical down towards the Earth's surface. The low angle surface is closer to the horizontal, which basically precludes sediment in motion. So we know that at a slope of 0 in a perfectly flat scenario, we have 0, and we'll define this in a second, 0 ability to move sediment. When we have very high slopes, we have some sort of high ability to move sediment. And it turns out that experiments have shown us, right, and these are really painstaking experiments where people basically place sediment traps on hillsides and like wait years for gophers to kick a bunch of sediment into it and measure how much sediment there is. We've found that there's approximately a linear relationship, unbelievable, a linear relationship between the topographic slope and the what we now will define as the mass flux of sediment or soil, whatever you want to call it. I'm going to use those interchangeably. And we define the mass flux of sediment in units of kilograms per meter of hillside per year. So let's think about that for a second. That's how many kilograms of stuff move through each meter-wide section of hillside in a given year. All right, so it has intuitive meaning, even though the units feel a little weird. And the reason we use units like that is because we don't just want to say, well, there's a certain number of kilograms per year, because then that depends, of course, on how big the slope itself is, right? And a tiny narrow slope would not be directly comparable with a big wide one, right? So we use these units of kilograms per meter per year, where the meters refers to a meter of width along a contour of the hillside. So how much sediment, how much mass of sediment, how many kilograms of sediment are moving through some 1 meter wide gate per year. And it turns out that our best experiments show us that at most hill slope gradients observed in nature, that relationship is linear, which is to say that slope has a linear control on the mass flux of sediment, or in other words, every increase in slope gets you an equal and proportional increase in the mass flux of sediment. So we know that this is a linear relationship, right? That's been revealed to us through really nice field experiments that people have done. So, and we know something else important, which is that this is a linear relationship anchored at the point 0, 0. So with that in mind, we can write, I think, I'll change it to say we can write, so there's no doubt about it, an equation, a simple one, that describes this line that describes this relationship between slope and mass flux of sediment. So what would that equation be? We know two important pieces of information, which is that this relationship is linear, meaning it's defined by a line, and that it goes through the point 0, 0. So what would this relationship be between slope and mass flux of sediment? What equation describes this line? You have all the information you need to write an equation that describes this line. How would we do that? What's the equation for a line in general? Like what you learn in algebra class or whatever. Well, that's the slope, right? So that's going to be part of it. But what's the form of the equation for a line?
Like y equals mx plus b.
Perfect. Yeah. So let's cast it in those terms. So what we're after here is we want to describe the slope flux relationship with an equation, right? We have some graph that I've drawn and we want to describe it with an equation. We know that the equation for a line is y equals, I don't know why they chose these letters, but I learned it exactly the same way. Y equals mx plus b, right? So let's first replace these variables with ones that we are actually caring about here. So let's call slope s, and let's call flux little q. I know that comes out of nowhere. It's just like what people do. I don't really have a good explanation for it. But it doesn't matter. We could call it banana. It doesn't matter. It's just going to be little q. So if the equation for a line is mx plus b, typically, what is the equation for this line with these variables?
Y equals sx plus q.
You are very close. So slope is our substitute for what so let's first diagram this. Maybe that would be helpful, right? So what is y in this case? What is y, like in words? Like when somebody tells you this equation, what is y referring to?
How much sediment is
Yeah, so in our case, totally, but like just as a generality, like what is the quantity y in this equation? Like when you're looking at a graph and you say it's described by that, what does y refer to?
Height?
Yeah, the y-axis, right? The dependent variable, right? The thing that's plotted on the y-axis. Oh, man. Gotta stop throwing the eraser on by accident. Okay, so the dependent variable, right? And in our case, you're exactly right. In our case, the dependent variable in this relationship is the mass flux of sediment, right? There just is some topographic slope. It is what it is. And our flux is what's responding to that. So in this equation, sort of the canonical equation for a line, what is the independent variable? What's the thing that does the controlling? What letter in this equation?
B.
Not quite.
X.
X. And you typically see, hold on, if I talk while I'm trying to spell independent, we're going to be in big trouble. Independent variable. And we typically see this plotted as like x is plotted on the x-axis and y is plotted on the y-axis, right? So that's why we use these letters. So this equation for a line is describing some relationship between some independent variable x and some dependent variable y, right? That's all it's doing. And you just get taught this equation like in algebra or whenever. So what then are these letters m and b? Let's start with m. What is m? Like mathematically, not in our case, but what mathematically is m?
Slope.
The slope, right? The slope of the line. slope of the line. So what does m equal when a line is flat? 0. What does m equal when a line is vertical?
1.
Not 1.
Undefined.
It's undefined, right? So it's infinity, basically, right? Because your rise is infinite relative to your run, because your run is nothing. But a slope of 1 is 45 degrees, right? When your rise over run, your rise and your run are the same. So m is the slope of the line. And now we come to the tricky one. What's b? Mathematically, what is b?
Intercept.
Come again? I think that was right. I just didn't hear it.
Intercept?
The intercept, right? The y-intercept. So unbelievable. Okay. Y-intercept, right? How do we know this is the y-intercept? Well, when x equals 0, the value of y equals b, right? That's the y-intercept. So this is what the equation for a line is sort of generally in math world. So now, how does that translate to our problem? Like, what equation can we write in terms of slope and flux to describe this line right here?
Be ms plus q.
Let's see. So you are close. So what do we put in place of y? What's the dependent variable in this case, or the thing that gets plotted on the y-axis?
Q.
Q, right? So we know our equation, so sort of our line's equation is, so we know Q has got to be in place of y, right? It's the dependent variable. It's the thing on the y-axis. So Q equals what? We're not manipulating anything here. We're just replacing this equation with letters that are familiar to our problem. Q equals what? What governs the sediment flux?
Slope.
Right, so the slope of the line, which we'll continue to call m for a second, right? There's a convention for that, but it could be any letter. And then what's the independent variable here? Slope, right? The slope of the topography. And then what is b, the y-intercept? In other words, what is the value of q when s equals 0? 0, right? So our y-intercept is 0. So this is telling us that in words, right, this is not complicated. It's just a mathematical statement of something we know to be true from the graph, which is in words that our mass flux of sediment per unit width of hill slope per year is linearly proportional by some slope term m to the topographic slope, right, or how steep the topography is. When the topography is perfectly flat, that's slope equals 0. We know that flux equals 0 in that case because all the gophers like fill in each other's houses or whatever, and we end up with no topographic change, no net flux. And as slope increases, we go from a low angle hillside to a high angle hillside. Our hillside is more in touch, or more in touch, closer in orientation to the gravity vector pointing downward, so we have more and more biased transport in that direction. So as slope increases, so does the mass flux of sediment. And the only change I'm going to make here is just there's kind of a discipline convention for what we call this term for the slope of the line. and we typically call that K, right? So we can define the slope of this line as rise over run, and we typically call that K. Don't know why, it just is. So the equation we're left with is the equation for a line with a y-intercept of 0 and a constant that governs that relationship that we call, helpfully, K. So what would this graph look like then if K were 0? If there were 0 rise per unit run, right? That's what that would mean in words. What would this graph look like if K were 0? It would be flat, right? And in fact, it would be a flat line at a flux of 0, because you would say Q equals Ks, K is 0, so Q is 0 every time, right? So if there is, if that K term is 0, we have no flux. If K is very, very, very large, we have a very steeply sloping line, right? That means that for every unit increase of slope, we get a huge jump in our sediment flux. So that leads us to call K is the soil transport efficiency, right? And there are a variety of words for this. This is just the phrase that I like. And I think that phrase makes sense, right? Because if soil transport is very efficient at a given slope, the flux will be very high, right? That would basically mean that we have some steep line, meaning that even at low slopes, we can move a lot of stuff. If our soil transport is very inefficient, why might that be true? Well, that could be because our soil is very sticky with lots and lots of clay. It doesn't really want to move. That could be because our soil is somehow shielded from the forces of erosion, maybe by grass or like geotextiles that somebody put down or whatever. If soil transport is very, very inefficient, or if K is very, very low, we end up with a line that is more flat, right? So we can diagram a couple of cases here. So we could diagram a case, gotta stop doing that. We can diagram a case where we have some low angle line, and we would call this low transport efficiency. Similarly, we could say, well, in a place where maybe the gophers have extra strong legs, and so they kick the sediment really far when they're digging their dens or whatever. I don't even know if it's called a den in that case, but it doesn't really matter. We could define a line that is steep, right? And we would call this a case of high transport efficiency. So there's only one sort of variable at play here, right? And it's this transport efficiency term K. The relationship between our topographic slope and the flux of sediment that will ultimately move down that slope per unit of slope width per unit time is governed by this parameter that's called the soil transport efficiency. So that can be affected by all manner of environmental things, right? The fact that you might have different species of plants and animals on one slope versus another, right? On one slope you may not have trees, and so they can't fall over, and so they can't move stuff. On another, maybe somebody hunted out all the gophers, and they can't dig, right? There are any number of reasons. Maybe you're in a place where it's too warm to have ice lensing that pushes the soil up and lets it down and kind of seesaws it on down the slope, right? Any number of reasons why that soil transport efficiency might change as a function of the ecology of a place, material properties of the soil and sediment, might change as a function of climate, for example, whether you have freeze-thaw cycling or not, and why we might observe different relationships across Earth's surface between slope and mass flux of sediment downhill. So what we're after here is some equation, and we found it, right? Some equation that describes how the shape of the landscape and the amount of sediment that moves across it are linked, right? That's what we're ultimately after. The shape of the landscape is defined by the slope, right? Or whether it's horizontal or steep. And the amount of sediment that moves down that particular landscape is defined as our mass flux, or our flux of sediment, or kilograms of sediment moved per unit width of the hillside per unit time. So what we're going to do next time is we're going to kind of take this math a little farther and figure out how we can actually calculate how the landscape will change its shape over time in terms of erosion and deposition of sediment, knowing what we now know about the processes that are active on a hillside and how efficiently sediment is moved. So I've got one last thing I want to do just to kind of prime us for next time. And, oh, that is not what I was after. There we go. And that is to look at these two landscapes, right? So what are we looking at here? Like, what kind of data is this? How are we visualizing? I mean, these are obviously places on Earth's surface, but like, what are we actually visualizing here? What are these called? What kind of data, like how did we even get this information? How can we look at a place in Oregon?
Satellite data?
Yeah, so this is data on land surface elevation that was collected by, often it's satellites, it sort of depends. Could have been an airplane, I think it was an airplane in this case, but basically by shooting sound or light waves down at the Earth's surface and measuring how long it takes them to bounce back, right? You shoot a light wave, it hits a peak, it bounces back faster. You shoot a light wave and it hits a valley, it takes longer to get back to your plane because it traveled farther in both directions, right? So it's a really astonishingly cool technique, I think, to actually get a really high resolution sense of what the topography looks like in these landscapes. So now I just want to ask you, given that we have this elevation data that we're visualizing, let's think about what are some differences between these two landscapes? These patches we're looking at are similar sizes, right? Here, about 1 kilometer by 1 kilometer. There, a little bit less, but not too much less. What do you notice, just anything you notice about the differences between these two places?
Different slopes.
Yeah, different slopes, right? So you've got sort of a number to help you with that here, where the average slope in the Oregon Coast Range is quite steep, about 0.75, again, meters per meter. So if you convert that into degrees, if 45 degrees is 1 meter per meter, this slope is just a little less than that. So that's pretty substantial. That's like black diamond skiing type of slopes. Whereas in Gavilan Mesa, you have an average slope of about 0.4, so a little over half. So what else besides their slope? And we see this reflected in the topography, right? This just looks steep. That doesn't look so steep. What else? What else is different?
Relief.
The relief, right? So what is relief?
I don't know, you want to tell us?
What might relief be given what we're looking at here? We have high relief up here, 320 meters. We have low relief here, about 120 meters. What could possibly be, what might relief be? Another term people use is topographic relief.
Is it like the change in elevation or slope?
Perfect. Yeah, the difference between the highest and lowest point, right, in the frame. So that's just to say that if we look in this entire square of Earth's surface, the highest point is 120 meters above the lowest point, right? So maybe, I don't know, it's this or something, 120 meters above the lowest point. In the Oregon Coast Range, the highest peak we're looking at is something like 320 meters above that lowest valley. So differences in relief. We can also define the average relief of any hill slope, right? Just the difference between any given ridge and its closest channel. Similar measure. what else is different about these? There's one more thing I'm looking for. What else is different about these landscapes? And it's, unfortunately for you all, not listed in text beside the images. Yeah.
The top one, like, it has sharper peaks, while the bottom one's more rounded.
Yeah, so that's what I'm after. So how would we describe that? Like the Oregon Coast Range example has these really sharp peaks, right? It's almost like what we're trained to think of when we think of a mountain, right? Like a kid draws a mountain. You know, this is like a kid's first drawing of a mountain. Down here we have something that, to be honest, looks a little more Appalachian in some sense, right? Like rounded off mountain tops that grade a lot more smoothly. So what is that, like how could we define quantitatively, and we won't dive into the math until next time, but how might we define quantitatively that difference? Well, we could come up with a metric. So if we kind of outline one of these sharp divides, and we outline maybe this drainage divide here that's much smoother, we could presumably come up with some metric of curvature, right? Or of how much our slope changes across this divide, right? Because in the Oregon Coast Range, the mathematical equivalent of what Isaac's talking about is just saying, well, to say a peak looks sharp is to say you go from a high slope in one direction immediately to a high slope in another direction, right? In the opposite direction. That's what mathematically a sharp peak is. To say that a peak is relatively flat means that it takes some distance to go from a reasonable slope on one side to a reasonable slope on the other. Because of that distance, we have a more rounded off peak, right? So the mathematical terminology here is that we have high ridgetop curvature in the Oregon Coast Range, which is to say that we undergo, as we cross this red line I've drawn, we undergo a change from a steep slope this way to a steep slope this way. In this Gabilan Mesa, or this more gentle looking or smoother looking case, what we're looking at is low ridgetop curvature, which again is to say that it takes some distance. The change in slope over distance is lower, right? It takes us longer to undergo some change in slope across this divide here or this ridge than it does across that ridge there. So we can define a few things that are different about these landscapes. There's different relief. The Oregon Coast Range one, by the way, looks all fuzzy because it has a lot of trees and they show up in the data. No trees to speak of here. That's one difference. But most critically and most important for our purposes, this Oregon Coast Range image has high ridgetop curvature, and we see low curvature or low spikiness of the divide, right, whatever you want to call it, in this California case. So what we're going to do next time is mathematically describe why that is and how that relates to the transport of soil, and we're going to quantitatively link processes of soil transport to the shape that landscapes take. Thank you very much, and please come to office hours if you need help with the problem set today. Have a good weekend.